record. You have the clicker.
I do.
Which works.
Okay.
And I think you're good to go.
Excellent.
Okay.
So I'm gonna let you stage manage everything.
Thank you, everybody, for your extraordinary patience. This is going to be a talk that is more than worth waiting for. So great to have you. Welcome to the April 12th CDAR seminar, and my old friend and collaborator from decades and decades.
I think my age is decades and decades and
A
decades.
really long time. Roger Stein visiting us here from NYU, talking about a few useful results using the ROC curves and the ROC. That's dash AUC.
The area under the curve.
Area under the curve. Okay, take it away, Roger.
All right, so first, if you're online, you don't know this, but I'm looking at a room totally packed with people. And it's the first opportunity I've had in 2 years to give a talk in person. I've given about 30 talks in the last 2 years, and this is the first one in person. So I'm very excited. I'm also excited because I'm presenting 2 papers that I've been working on, neither of which is fully complete, and for which I would love to get some feedback, or on which I'd love to get some feedback if you have it. I'm going to talk about a few different things. The first thing I'm going to talk about is some comments I got back from a referee on the paper, suggesting that I spend more time introducing the notion of an ROC curve, because some folks may not be familiar with it. It's quite prevalent in biomedical research and in machine learning, statistics, and credit, if you do finance. But for a lot of other fields, it's a kind of a new topic, or it is a topic that goes by a different name. Yes, Lisa.
ROC, that's receiver operating
Yes,
curve.
it's I'll walk through that. But yeah, it's a receiver operating curve. It's a way of measuring the discriminatory power of statistical model. So then I got some new results from 2 different papers. The first and more interesting in my view is a method and a result that allows us to combine disparate to combine 2 different models estimated for the same purpose, but on different data sets which do not overlap with each other. And I'll explain what that means. But it's particularly useful if you're working in, say, an industry and you have the opportunity to get some new data, but the new data doesn't cover your whole data set. And so you have to join some records in your existing data set with some new records under the assumption that you're going to have a better result for your model, but you don't know that. And so you'd like to figure out how good could the model get, given where I am today, to determine whether that's. The second result is a geometric one, and I'm going to say it again, but the results are trivial in hindsight. But it turns out that if you get just one true positive, true negative point, as you might do, for example, when reading the back of a take-home COVID test for sensitivity and specificity, if you get that, it turns out that you can still calculate an upper and lower bound geometrically or through calculus on the ROC curve that would be obtained. Now, hopefully, after I've gone through the ROC stuff, for those of you who aren't familiar with ROC curves, you'll understand why I think that that's useful. So that's it. That's what I'm going to talk about. We got started late. We had some technical issues. So I may have to skip a little bit at the end, but I excel at doing less than expected. So hopefully that'll be okay. Okay, so when we talk about validating models, it's always important to define our terms. In the early days of credit modeling, where Lisa and I did a huge amount of work in industry, some of it that was useful, we find that in the early days, there was not a clear definition even of what a good model was, what made a model good. Let's say you're trying to predict bankruptcy. We didn't know how to measure that. People would tell stories. Oh, look, my model predicted this default, a year before it happened. It was anecdotal. And then in the early 2000s, we did a bunch of work that tried to formalize that using some techniques that have been developed in other disciplines and porting them to credit. And that led then to a need to define exactly what we mean, because it turns out when you build a model, there are a couple things that you're interested in. The first thing is power. If I've got good things and bad things that can happen, and I've got a bunch of data for which I don't know which of those things happen, but I'd like to predict that, a powerful model is very good at separating into two classes, those that are bad and those that are good. And a weak model doesn't do that as well. You can think of that as being, how much you rely on the model for a particular prediction. But the other side of it, by the way, that's related to the notions of model variance and some other things. And if you're working in continuous space, then you can talk about measure of correlation to get similar measures of power. In calibration, tested calibration, we care primarily about the accuracy of a predicted probability. So if we've got a multi-class problem, we predict a probability for each class. We'd like to know that those probabilities can be relied on, for example, to price a loan or to determine whether to let somebody into a stadium or something like that. That's calibration. Now, it turns out that in most cases, it's much easier to improve a model's calibration than it is to improve the power. Because the calibration can be fixed literally by calibrating if you've got good data. Power, we don't really know. You have to build another model. You have to make your model better in some way, and that's very hard typically. By the way, I should mention calibration is related to bias and prediction error and such like that in the literature. Now, if you're interested in this difference, this dichotomy, many years ago I wrote a paper that kind of discussed it quasi-technically. But in that paper, there's an example of a very powerful model that was poorly calibrated that would have been selected by accident if you had chosen calibration rather than power. Okay. Hey, John. Hey, Dan. All right. Now,
Hi, Roger.
let's move on to our next. I don't know, this is not working as well as
Yeah, I don't know if the buttons, they seem
It's
to.
this button, right?
Yeah, I think so, yeah. But I think sometimes it switches between Zoom and.
Okay. I have another clicker if I can. You want to use that instead?
Yep.
Okay. Oh, geez.
You want?
You said it's
Hey.
far easier to improve model calibration than to improve model caliber. I saw that on the previous slide.
Oh, power. It should be power.
No, you did. Sorry.
Okay.
You did model
Yeah.
power than caliber.
Yeah.
Far easier to improve calibration
Yes.
than power.
So I'll give you an example.
Yeah.
Let's assume that let's assume that I take.
The issue is like there's no cursor, so I'm sort of.
So just click on that.
Go up. Yeah, can you get up there?
Yeah, but you can't see, you can't. I mean,
There we
sort of.
go. Yeah, I don't know. So to your question, Lisa, if imagine we have a model that perfectly discriminates between good things and bad things. In other words, if this thing predicts it's bad, 100% of the time it's bad, 0% of the time it's good. If it predicts it's good, if it predicts it's good, 100% of the time it's good, 0% of the time it's bad. That's a very powerful model. And let's say, though, that we calibrated that to the original training data set. So we've got, maybe we use a matched sample, for example. Now, the real baseline probability is different than that matched sample, right? So let's say the probability of a bad thing is really like 3%, but our sample has it 50-50. So the probability is predicted by that model for uncertainty, for zero knowledge. In other words, the model did not know what to do with a certain record. It would predict 50%, 0.5, as like flipping a coin. I don't know which of these two it is, so I'm going to predict the probability to be 50%. Now we know that the real probability of 50% would be quite extraordinary, given the real base rate is 3%. Now, if we tested the model's predictions in a probabilistic sense, we find that was a horrible model, even though it's perfectly discriminating. Right?
You're saying that the test results depends on what you tested on?
Well, not just what you tested on, what the models, how the model's prior what prior distribution the model learned on. Okay, so for example, if I were using that model I just described in the real world, I would get extraordinarily high probabilities of the bad thing, even though we know the base rate is very low. If I want to fix that, I can calibrate to the right base rate a few different ways. And if I do that, now I've got a really well-calibrated model that's also really powerful. Let's go the other way. Imagine I've got a model that has no power, but it's perfectly calibrated. It always predicts the mean probability, the baseline probability. So it's never, if you look across a huge sample, it's always going to give you the right answer on average, right? If I want to make that more powerful, I've got to build a new model. and figure out the underlying mechanism that's driving the differentiation between these two different classes. That's a much harder problem than fixing the calibration.
Okay.
Okay, so sorry. Okay, so what is an ROC curve? Let's start and imagine I worked a lot in credits, and so did Lisa. So I'm going to talk about a default model, a model that predicts whether a company will default on a loan, let's say a year in the future. And to do that, what I do is I take a data set. And if I've got two models, I make one copy of the data set. So I've now got two different copies of the exact same data set. And then what I'd like to be able to do is order all of those records from the most likely to default to the least likely to default. If I were to do that, on one side, I would have the most likely to default. And on the other side, I'd have the least likely, that says 2 underneath Dan's thing, to default. And everything else will be somewhere in the middle, right? So let's go back now. And I'm going to take my two models, model X and model Y, identical data. I want to point out these are all the same, in this case, borrowers. And then what I'll do is I'll score all those borrowers with my model. Score everything with model X, then I'll score everything with model Y. Let's say I do that, and then I sort by the scores. Okay, so I have the very worst scores on this side, and I have the very best scores on that side.
Now the orders are different.
Well, the orders are different, of course, but let's wait and see that. Yeah, with two different models. If they're not, if the models aren't identical, say it differently. If the models don't produce identical results, then the ordering would have to be different. So let's see what that looks like. So we've just sorted them now by those model scores. We can now get rid of our models. We don't need them anymore for this particular exercise. And now I've got a whole bunch of records in different order that are sorted by the predictions of each of the models. The top one's model X and the bottom one's model Y. The next thing I can do is actually look at what happened. And if I do that, here's what I find for model X. The red face smileys or frownies are the ones that defaulted, and the yellow ones are the ones that didn't. So that's what model X looks like. And that's what model Y looks like. Now, if I were lending money, which model would I rather use? Well, it's pretty obvious in the way I've drawn it, right? I mean, you know that by using model X, most of the bad guys are going to be clustered together in the bad part of the distribution, and most of the good guys are in the good part. And in model Y, they're kind of scattered throughout, not as effectively. So we would say this model is better at differentiating by score between the good ones and the bad ones. And this model is less good at doing that. So model X is better, model Y is worse. And we would say model X is more powerful than model Y. Now, the scores don't have to be probabilities. They can be numbers from 1 to 37. As long as there's an ordinality to them, I can sort by them. But these could be producing ridiculous probabilities and still be very powerful.
Yeah, but Roger, if I were speaking plainly in English, I would say the top one seems colloquially more accurate. You know, but the word power is kind of a term of art in specific statistics.
Well, it's a term of art in two directions.
But you haven't defined it yet.
Yeah. Well, I did actually in the last slide. I said power is the difference between, is the ability to differentiate good from bad, two classes. Now, you're right, though. We could be talking about the power of a statistical test, which is, if my sample size is big enough, and if I design the matrix, the design matrix correctly, and so on. Different definitions.
So you're using the word power here more informally, not in the sense that I'm used to, where you say the probability of rejecting.
In this domain, it's actually formal, but it's different than the statistical. Yeah.
But, I mean, I think of power as the probability of rejecting the null hypothesis.
Well, let's hold that thought. We'll get there in a second. Okay. So if these are my good guys and these are my bad guys, the red ones or the ones on the right are the bad ones, and the ones in green or on the left are the good ones, for those who can't see color so well. We can actually use that information to do a kind of quick calibration. If we want to get to probabilities, we can do that from our base rate in the training sample. and it's trivial to do. What I do is I just set a cutoff point somewhere, and I say, my model will call good everything to the left side of that cutoff and bad everything to the right side. And then what I can do is I can actually count up. How many times did I say something bad happened and it was really bad? And how many times did I say something good happened and it was really good? And so let's say I did that. So here's a bunch of good predictions that had a good thing happen. And here's a bunch of, there were 45 of those in this particular example. And here's 5 examples where I predicted good, but the bad thing actually happened. In our case, we're talking about default. So I said, make the loan, but the company defaulted. Okay. And we can go the other way as well. But just to point out that if I were to just do some very naive calibration, what I would find is that the average probability of a bad thing, given that I said thumbs up, is about 10%. And I can do the same thing down here. What's the probability of a bad thing, given that I said thumbs down? Well, in this case, there are 60. And so what I get is 83%. So now I've naively calibrated the model to produce probabilities. I needed probabilities, but I have to be aware that these probabilities may still need to be adjusted if the baseline in my testing sample is different than the baseline in the real world. However, we can get to probabilities. Now, how would we set a cutoff? There's a good literature on this. And it turns out you can also set individual prices for each of these things based on the ROC curve as well. And there's some literature on that. But let's say that we're doing this by eyeball. And so I set the cutoff for model X here and the cutoff for model Y there, for whatever the reason I chose them. Maybe in this case, in the Y model, I care more about catching bads than I do about letting goods go by. So I've done that. I can then do the same trick and cut to sorry, that should be 3, not 8. A typo on my part, as I promised there would be. We can now do the same thing and aggregate these up and get our probabilities. It's often useful not to think in terms of smiley face, we think of numbers. And in fact, we often want to convert those numbers to probabilities or frequencies, which are empirical. And what we can say, though, is if I use the cutoff for Y that I chose, and I use the cutoff for X that I chose, it's pretty easy to see which model I prefer. Because the diagonal, the green part, if you can see color, the green part, the diagonal is uniformly larger for this model. So I get more right. And then conversely, the off diagonal, the red part, is uniformly smaller for this model. So this model is not only producing better good predictions, but also fewer bad predictions. So we can take that. By the way, just to observe that there are many statistics that can be derived from the transition matrix, or sorry, the confusion matrix, or sometimes you may see it referred to as a contingency table. All of these typically can be defined with just 2 pieces of that matrix, because the other 2 are implied. And the piece you need is true positive rate, or 1 minus the false negative rate, and a corresponding for the true negative.
So can I ask a question? So in many settings, including the credit risk setting, the loss function is asymmetric.
Yes, so I'm going to get to that. And that, by the way, if one were forced to do a cutoff, to use a cutoff rather than doing pricing natively, the optimal cutoff is the one that would actually either minimize that loss or maximize the profit. And again, I'll give a reference, but there's literature on that. I want to skip over that because it's not that germane to what we're doing. But what you raise is actually a valid point, I believe, which is that there's no guarantee that I chose the right cutoff arbitrarily. And so you could ask, what if I chose a different cutoff? And that's actually a lot of the second paper. So if I have these true positive, false positive rates, and so on, I can convert those into frequencies. And what I can do, if I have the true negatives over here and the true positives over here, in our case, non-defaults and defaults, I can actually take a matrix and calculate all of those quantities directly from the space that I have there. And in this case, that is showing us exactly the cutoff I just showed you before. So that's exactly the model that we just talked about. I think that's model X. Yes. I could also do that for a different cutoff. This is to Bob's point. I could do it for a different cutoff. And that would be there. I could do it for another different cutoff, and that would be there. In fact, if I were to just calculate every possible cutoff based on my data, I'd get a curve. And that curve would look like this. And that's called an ROC curve. Now, from any model that I look at, I can get a cutoff and I can get a point on this curve and I can plot the curve. Now, it turns out it's easier to plot the curve differently than by doing all those contingency tables, but that's okay. So again, all the quantities I want for any cutoff, I can get from the ROC curve. So even if I don't know what the right cutoff is, I can still prepare for it by drawing an ROC curve. Now, if I were to plot two different models, ROC curves, models with an S apostrophe, ROC curves, a random model will look like this. And what that means is that if I want to exclude 20% of the defaults, I got to basically give up 20% of the goods as well. If I want to give 40%, I have to give up 40%. I'm not really adding any value. I'm just basically cutting my data in half or something like that, or in fourths or eighths. A very powerful model, or reasonably powerful model, might look like that. It's bowed out to the northwest, and what we can say is that it, kind of fills up a lot of that space. A less powerful model would look like this. We call it a weaker model, and we can see it's also bowed out, so we know it's not random, but it's not as non-random as the other one. Now, here I'm bringing it all together for you, Bob. If I have these two curves and one is dominating the other one at every point, it is guaranteed that regardless of the cost function I choose, the top model will be preferred. And the reason for that is simple. If I want 40% of the defaults and I go here and I come down, I'm going to have to give up something like 8 or 9% of the non-defaults. So those missed business opportunities. If I want to get the exact same reduction in defaults using the lower model, I have to give up something like 19% of the goods for the exact same benefit on the bads. So I'd always prefer this one for whichever one I want. And by differentiating our cost function, we can find the exact point on that curve that's optimal for a cutoff. But we're not going to do that today. Now, again, just to give some intuition, remember that the more bunched up the bad ones were on one side, the more bunched up the good ones were on the other side, the more powerful the model is and the higher the ROC curve will be. And so if I've got one model that can differentiate this way, the choices for cutoffs are probably somewhere in this region here, although there's a lot of overlap. If I figure out a way to make that model more powerful, then what I'm actually doing is that, and making the cutoff much clearer, because I'm doing better differentiation, better separation. Differentiation in the colloquial sense, not in the calculus sense. So now we have a curve, but it's sometimes convenient to be able to summarize that in a statistic, a single statistic. And by convention, we summarize that through what's called the area under the curve, the AUC, often abbreviated just as A. And there are really two ways to think about this quantity. We can think about it the way we learned in calculus, which is that we want to integrate the area above that random line and add 0.5 to it for the part that's random. And what you can see is basically this integral is telling us how much the space is taken up above the line by the model. That's one way to think about it, and it's a valid approach. In fact, I'm going to use that notion, that intuition, in the second set of results. A lesser known, but I think more valuable way to think about this is that the AUC turns out to be the probability that if I took all my bad records in one bag, all my good records in the other bag, and I reached in randomly and pulled a good one out, reached in randomly and pulled a bad one out and compared them, it turns out the AUC is also equivalent to the probability that the the bad result will be rated worse than the good result by the model. So I'll say that again. If I've got two bags of data, one's all the bad results, one's all the good results. By bad, I mean the bad thing we're trying to avoid for business or medicine. Good, I mean the good thing, like a healthy patient or something like that. We reach into the healthy patients and pull it out, and we reach into the maybe afflicted patients and we pull one out. And when we compare them, in general, this is the probability that the good ones will have better scores than the bad ones. Now that result turns out to be really helpful for what we're about to do, and I'll show you why. So again, you can think of that as being just sort of like, what's the probability of comparing these two distributions? Okay. So this, if you crank through the math, this basically gives you the empirical frequency if you were able to measure every comparison. We have some finite number of records and compare every bad to every good. And then you calculate that average over here, where M is the number of bads and N is the number of goods. This has a strong foundation in non-parametric statistics. It's equivalent to the Wilcox and Mann-Whitney statistic. Serendipitously, they were developed independently. And we can take advantage of that. I use this top result for the top relationship for the second set of results. And I use the bottom relationship for the first set. I put them in this order because this is the way that people usually think about the area under the curve, and this one's a little different, so I want to start with that. One other thing I should mention, although everything I'm going to talk about involves AUC, the area under the curve, it is entirely possible that there are two curves with identical AUCs, and I'm showing you two right here with identical AUCs that behave differently. And in this case, Bob's cutoff question becomes a lot more difficult because, in this region here, we're not really sure what to do. And it turns out that we can create a convex hull over that will an expectation give us a better performance in either model. But if our cutoff is here versus here, we imply different models that we would select. So even though we're going to talk a lot about AUC, I just want everyone to bear in mind that, look, it's really possible that whenever you summarize something with a single statistic, you're throwing away information, and this is the information that we're throwing away. This is part of the information. All right, so I'm going to take advantage of a certain relationship that I actually stumbled upon when I was writing a different paper about noise in data published in 2015. But if I let n, the number of non-defaults, let's say, be composed of two subgroups with size ns and nb, and I let m be composed of two subgroups with sizes ms and mb, and without a loss of generality, I assume that they're ordered, which is all this says, so that whenever I have an index of one of the b's, those indexes will be uniformly higher than any of the indexes in the a's, the subscript a's. So let's say I do that. Well, it turns out then I can actually decompose the AUC into a series of smaller sums. In this sum, I'm comparing the so this sum here, I'm comparing the small n's, or sorry, the mn and m. Sorry.
MS.
Thank you. MS and NS of the sample, comparing them to each other. I'm going to add that comparing the MB and NB of the sample. And now I'm going to calculate the cross terms as well here. Okay. Now it turns out when the dust clears that this is just equivalent to the original A that we talked about a few slides ago. And I'll just point out that we should keep track of where these are running. That's a typo. These should both be, oh, that's right, these are right, I'm sorry. Yeah, so we should keep track of where those sums are running, because where they start and where they finish relates to this point up here, them being ordered. We could do it without that, but this makes it much easier. So there is no loss of generality, it's just that it makes it an easier result. So I'm going to use the fact that we can decompose the AUC into a bunch of smaller AUCs that we can add up. All right. Now, that's all the background. That's everything that we need to move forward at this point. I'm going to pause. Are there questions or anything from anyone?
One chat message. So Dan says,
Yes, this says from my good friend Dandy Bartolome. My recollection is that a lot of early neural network stuff was based on ROCs with layering and entropy measure rather than with contingency tables. There was very early work by Ross Miller with financial applications. Yes, and as it turns out, so Dan, thanks for that comment. And Dan's point was that you can, what you choose to measure when you're ordering things and how you choose to define goodness does not have to be the Mann-Whitney, Wilcoxon Mann-Whitney approach, but it could be something else. And I'll also note that the entropy stuff is closely related to the statistical notion of likelihood, and has some limitations that are also similar. Likelihood, as we just talked about earlier, talks about how well calibrated something is versus how powerful it is. Okay, so can we get rid of that thing so people could read the slide?
I think people who are on like Zoom can actually.
Oh, okay,
read the
good.
slide.
Yeah.
All right, good. Okay, so in some settings, it's useful to model subsets of the training data individually rather than estimating a single model. What does that mean? For example, assume that I was building a model for customer retention. And I have all my data from my transactions database. And then a vendor comes to me and says, hey, I can sell you alternative data. It's based on tweets and things like that. And also based on stuff we scraped from the internet. If anyone happened to see John Oliver's show this week, he talked all about that. It's really creepy. But let's say they come to us and they offer us to sell this data at a price. So we're happy about that. But it might be that that data is not available for every transaction in my every customer in my transaction database. So I've got a subset of transactions for which I've got the transaction data and the extra special data, and another subset where I don't. And we'd like to build a model, but we don't want to have to choose one or the other, because if we have to choose one, we have to choose the smaller model that doesn't have the extra data, because unless we're going to do some very, very fancy imputation, we're not going to be able to make use of that other data when it's missing. And so we have to build something really much more involved, or we could build one model called the big model, and we could build another model, the small model. The small model is based on just the transaction data, and the big model is based on the complete transaction data plus the extra data. So the model now becomes a two-step algorithm in which we first decide which data regime we're in and then choose the appropriate model. And in those settings, if I'm trying to decide whether I should buy this data, it's useful to understand, well, if I were to buy it, how good could my results get and how bad could they get? Because they could just easily get worse as they could get better, but there are bounds on that. And these next set of results speak to that. So just to give you some, kind of visual sense, we have our transaction data, we've got our vendor alternative data, and we combine them into two data sets, a smaller now set of the pure transaction data and an even smaller set of the join data in this case. So maybe we only had data on 30% of the total transaction flow. And so that data is over there. We're going to build a model using whichever algorithms we like for learning. And when the algorithms converge independently, we will get a new model for each of those different sets of data. So we've got this purple model here for the full data set, or the big data, the big model. And then we've got this blue model for the ones of our customers who only have information on the transactions, but nothing on the other stuff. And each of those models will have an AUC.
So, sorry, in the blue one, you didn't use the overlap.
Right. Yeah, it's hard to see. It's actually got shorter.
Yeah, no, I just wanted,
Okay.
I thought I understood that. I just wanted to make sure. Because you could have done a model on
The whole thing, yeah.
and you could have done a model on the subset for which you had extra data.
Yeah, and the reason I chose this example, because it's much clearer when there's no overlap. If the models overlap at some point, we get to that where they could cross over and there may be a better choice.
Oh, okay, I'm just trying to make
Yeah.
sure that I and everyone understands what you did.
Okay, well, is it clear so far?
Perfect.
Okay. All right, so now I bring in my switching algorithm, I get some new data. And I bring in my switching algorithm. And now I drop one of those data in, and it turns out that, or one of those datum in, and it turns out that that was a small data profile. And that guy there is a big data profile. And when I'm done, I want to know what's the combined performance of these two models. Now remember, each of these models produces, let's say, a well-calibrated score, but they're going to be interleaved in our data. So it's not a matter of simply averaging the two AUCs, because we're changing the relative ranking of each one of their items because we're adding extra stuff. For example, let's say this produces scores of 1 to 10, and this produces scores of 1 to 10. And we now have a fully ordered set of 1 to 10. We have a fully ordered set of 1 to 10. When we combine these, they're going to change each other's orderings, basically. Sorry, the orderings will be the same, but the overall ordering will be different. So for example, a 2 here may end up being somewhere, between a bunch of 2s up here, based on its score, maybe 2.2, 2.3, whatever. So they're mixed together. If we had full data, if we had all of this data and all of that data, and if the proportion of each was unchanging, we wouldn't need to do all this work that I'm about to show you, because we just calculate the true AUC on the empirical data.
Does it matter if the set on which I got the extra data that caused me to go from blue to the purple has some selection?
Yeah,
stuff
there's
associated with it, or does it have to be just random?
it's a lot easier if we assume no selection. In fact,
Yeah.
I'll show you in a second.
Okay.
Here's an example of that data. So here we've got a bunch of customer IDs and product IDs and product categories, and then a bunch of demographic data here, which is not available for this other customer. This customer is 197, and this customer is 1091. And here we have the complete transaction data. Everybody has that. And here we have the customer demographics data. And you won't be able to see this, but this customer is found in the database of the vendor. And this customer is not found in the database of the vendor. Now, for those of you who do this work, this is an embarrassingly common problem. It's endemic in the work we do. And so often we're faced with the decision, given that I can buy this extra data, but I can't test all the stuff together. Data is one of these things where once you know it, you kind of got the value out of it. So most vendors won't give you their whole database for you to decide if you want it or not. So it's interesting to find out, is it worth it? So I'm going to define some notation. Capital AB is the area under the curve for the big model when I have complete data. AS is the AUC for the small model. AH is the result of that little combining algorithm where I use both models alternating. A0 is the AUC for a random model. A0 is equal to 0.5. And A1 is the AUC for a perfect model, which is equal to 1. And then finally, gamma S is the proportion of the population that doesn't have complete data. Okay, Lisa nodded, so I'm guessing that's clear. So here's our first result. And you can see the appendix of the paper for the actual proof. But if I have these two models with AUCs, ABB, ASS, ASB, ABS, thinking back to that equation I said, you can decompose these things. So all I'm doing is decomposing these different data sets into pairings that pair either full data with full data, partial data with partial data, or partial data with full data, or full data with partial data. Okay? And it turns out that this mixing coefficient here is pretty important. But if I have done this properly, then I can make this decomposition. And again, we're not dealing with observation noise here. So we're assuming these are almost like deterministic numbers. This will give me the hybrid without ever needing to look at the data in aggregate together. So using the A0 and A1 notion, if I don't know what the big model's AUC is, the best I know it can be is 1. So I can substitute 1 in for AUC of the other one. And if I don't know what the AUC is, I can substitute the random AUC 0.5 for the other one. And if I do all that, then these are the results. So now I've got my first two sets of bounds results. And these tell me, and this is what they look like, or certain values A, B, and A, and gamma S. And there's, the hybrid, this is the actual thing we care about. And, you can see as the mixing coefficient goes to 1, we get, a positive result and the lower bound. And as the mixing coefficient goes to 1 over here, it goes to 0. 1.5. The ranges here, if I don't know the value of the model that I built with the extra data, then the ranges are actually constant given gamma S. So, this gives you the intuitive result that when gamma S is, so when gamma S is 1, in other words, we're only using the old model without the extra data, then there's no range at all. It's just the only value I can get, because I'm never using the other one, is the value that I got the first time. Similarly, if there's 0, then I've got the full range of possibilities, because I could actually improve by using a model that was 100% perfect, and so on. Now, what if we know the value of both models? For some reason that we've been able to figure out, we know what the AUC of the model using the big data, the big model using the supplemental data is. So let's say we know that. And I'm going to define that as AB, AS, where I know both of these quantities, the AUC on the big model and the AUC on the small model. This expression here will give me actually what that hybrid model turns out to be. And then we get the minimum and maximum there as well, where instead of substituting in 1 or 0, 1 or 0.5 for the naive model and the perfect model, we now substitute in the AB for the big model. Here are these results. And again, the algebra is not that interesting. And that's what that looks like. I'm not going to spend a lot of time on that. But I would like to give you an example. I've been kind of toying with this example that you have the opportunity to buy some data. So let's dig into that example. Imagine there's a credit card firm that has developed a fraud detection model, and that firm would also potentially like to acquire extra data to improve the performance overall of their model. So let's say that the firm's model does okay, got an AUC of 0.78 versus 0.64 for a naive model, and for a large data set, that's a very big difference. So they're happy about that. And then the vendor comes and says they can provide alternative data to forecast fraud. But the data is only available for about 25% of the borrowers. So, there's that trade-off. And then, Lisa, this is your point here, the little footnote. The firm also determined that there's no, the missingness is not informative.
It's not like they all live in Wyoming or something.
They could all live in Wyoming, but that might not be material. Whatever the result is, they've determined that the reason that you have or don't have data is basically effectively random with respect to this problem.
Yeah, but okay.
Now, one of the extensions is to fix that up and say, well, what happens if there is correlation and so on, but that's a different.
We'll have more complicated formulas.
Yeah, considerably more complicated. I know no problem for which adding correlation makes it easier. All right, so if the firm purchases the alternative data, how much of an improvement or decline in the performance of the model would switching provide? So we have this mixing coefficient here. So there's 75% because we only covered 25%. That would actually be covered by the small model. And the small model's AUC is 0.78 from our previous slide. We can crank through the numbers and we can find that the model could get worse. And if it got worse, it might go down to as low as 65, but it couldn't go lower. And the model could get great, better, and it would go up to 88, which is considerably better than 78. Except when we do the math, we notice that there may be some trade-offs to make. And I'll get to that in a second. Let's continue the example though. The credit card company, however they did it, estimated that if they can get their AUC up to 0.87, then that would be sufficient to pay for whatever the exorbitant cost of the data is. In a, from a cost function perspective, as Bob was talking about. So what the firm does is they say, give us a small subset of your data that we can match for our customers. We want to get a rough idea of what the AUC is. And the results suggest that when they add the alternative data to the data they already have on that small subset, the AUC goes to about 0.8, which is definitely higher. And let's assume that they have enough data that that's a both statistically and economically significant difference. So if it can achieve an overall AUC of 0.87 or better, the alternative model will pay for itself. And so now we have a target. Now we know what the big model's AUC is. We know what the small model's AUC is. And the question is, can we combine them to get to 0.87? Now you might say, looking at this at first blush, there's no way. There's no way that could happen because if I average these two, I don't get a number that's different than, or that's higher than 0.8. But it turns out because of that sorting, the resorting that happens when we add in these other numbers, you can actually go quite a bit higher and quite a bit lower. And you could actually differentiate those equations to figure out where that happens, the ones I showed you. So that's the thing, that's a new bit of information that we got. So we now no longer assume that the maximum the model can do will be will be 1, but we now assume it's 0.8. We crank through the math, and we notice that the target of 0.87 is still greater than the upper bound of the hybrid. And therefore, we decide not to buy the data. It's not going to be worth it.
I agree with you, Roger, your title. This is insanely useful.
Oh, thanks.
So but I do have a question. Is this really not, and not that it matters, because I love the way you're saying it, but is it really not known?
So both this result and the other result appear to be unknown.
I mean, even
You're going to be more shocked when you see the really simple second set of results.
I could use this thing all day long.
Yeah. So, I mean, when I say it appears not to be known, what I mean is I've talked to everybody I know that deals with ROC curves, and nobody's seen either of these results. This one actually came to me because one of the few people that I know who actually does more work with ROC curves than I do posed this exact question.
Yeah.
And he said, well, you've solved it in your 2015 paper. And I said, well, it's different. He said, but can you tell me what the answer is? And I went back and forth for quite a while.
I would figure, it's not, even if it is known, it's very useful to have it framed in the context of this commonplace problem.
Yeah, you can probably plot the upper bound, lower bound kind of things using gamma, right? How much,
Yes.
how much data do you want?
Yes, or how much, well, let me get there in a second. Actually, you're like what my students always jump ahead. They get really, not that you're a student, obviously, but.
She is a student. Don't
well,
even say that.
Well, sorry, you're not one of my students.
We all are.
You're not one of my students. All right.
No, it's imperative answer for my work, so
Yeah.
I'd like to hear it sooner.
Okay. All right, well, I'll help you out here. What can be done to make the data more valuable? Well, if the fender can improve its coverage by rearranging equation 7, they can figure out what the minimum coverage has to be in order to be useful.
Gives them a perverse incentive, though. Makes that up.
Well, yeah, the firm can also improve the model, the power of the big model, right? The firm could just do much more work on the big model or the small model to make them better. And the big model would have to get to be above this B star, which I'll calculate in a
I'm going to
second.
use this this afternoon.
I'm glad. Well, keep in mind, I have not yet talked about the non-deterministic nature of the things we observe with error.
Yeah.
So, you can easily calculate confidence intervals on all these numbers. And the means will be slightly different. All kinds of things will change. But as a first approximation, this is not a bad first guess. If we were to do that experiment, what we find is, I don't know if you'll see because it's covered on our side.
Oh, no. Well, just tell us what it's.
I believe that was 0. So yeah, I think it was, you had to get the coverage down to 7.2. I think, yeah, your coverage, so you had to improve coverage by about 3%.
We could just read it right off.
Well, we can't though, because the thing's blocking it.
Even when there.
Yeah. There we go. But now move it, so 17, I was right. So move it somewhere else again. Actually, move it way down. Keep moving it down. So there's the other solution. Instead, if the firm said, well, let's do extra work, much more expensive, by the way, because they have to build new models and resources and all that stuff. Whoa.
Sorry.
So the firm has the option instead of buying the data with the coverage that the vendor currently has, but somehow increasing what they do with that to get above 0.8 to get to 0.9. To my eye, changing coverage is a much easier problem
It just depends.
than building a better model.
I mean, it really depends on how hard it is to get coverage.
That's a fair point. Yes, I'll take that point.
Depends.
But keep in mind, we're talking about a change of about 2% in coverage here, and we're talking about 10 points of AUC here.
Well,
So
you don't know what it takes to go out and get.
I agree.
You're a model builder, so you
I
know
agree.
why that's-
So if it turned out it
No,
was
coverage
really,
getter.
I actually was a coverage getter. You remember CRD. So if I found that it was very expensive, I might try to figure out ways to make the data more
Yeah,
useful if I
it
were a
doesn't
vendor.
really, right, anyway, it's a stupid
Yeah.
conversation because you've given,
Yeah.
you've shown the trade-off.
Okay,
Figure out.
so that's that. And that was the first set of results.
Yeah.
All right. Any questions before I go to the second set? How are we doing for
I
time?
do, because I just want to say want to leave time for questions and we do have to leave at 12:30.
Okay, so this is actually, the good news is, this is incredibly simple stuff. The next one. I mean, no, I'm not being modest. This is incredibly, the reason I put the first one first is I think it's much more interesting, but the second one's also really useful. So let me get there quick.
So can I ask one quick question?
Yeah.
So you had a range of possible values that combine two models together. And, you said if the upper part of the range is below the target, then you won't do it. But suppose the target's in the middle of the range. How do you
The
decide?
target's in the middle of the range.
Well, the cost of buying the data is now enough so that the upper,
Oh, the upper bound is met, but you could still hit the lower bound.
yeah,
Yeah, that's then a business decision. And when I get to this set of results, which use that calculus representation of the AUC, I'll show an example of one kind of calculation one might do in that regard. But I mean, at the end of the day, there are still business. Oh, sorry. What this can do is clearly rule out options. It can't tell you that the option is necessarily going to pay off in most cases. I mean, in rare cases, you will get the lower bound above what you have now, and that's a rare too. So it's a no-brainer if the upper bound is below what you need. It's a no-brainer if the lower bound is above what you need. Everything else is business decisions or medical decisions and so forth. So this is a second paper, which is currently under review. And imagine you're told now, totally changing hats. We're no longer talking about business, we're talking about lives. Okay, so now we're talking about COVID tests. And we have two COVID tests that we can use. Let's say we're a municipal government, we've got to get COVID tests to everybody. So we've got to choose which COVID test we want to buy. And for the time being, let's ignore cost functions because health and cost is very complicated. Let's just assume that the tests are priced the same for the value they provide. Each test is only described in terms of its sensitivity and specificity, right? And we don't know anything else about it. And let's say these two tests perform like this. Now, either one of those tests looks really good, by the way. And that's a very, very strong result. But it's not at all clear which test is better because the true positive rate on test A, sorry, the true positive rate in test A is above the true positive rate on test B. But did I write this wrong? I think I wrote that backwards. I think this should be down here. I'm sorry.
Yeah, that would be better.
Yeah, well, we get to the other example. When we get to the actual worked out example, I think we do.
Yeah, so we have to switch everyone in your minds, but we're.
Yeah, just flip these two and then you'll see, then you'll see the problem. Okay, so in our space that we drew before, that's what a single true positive, false positive point looks like, or true positive, true negative, however we want to do it. These three curves are three of the infinite number of curves that I can draw that start at 0, cross through this point, and end at 1. If I impose regularity conditions like monotonicity and the curve being above 0.5, it reduces that space, but it's still countably infinite, assuming that these are real values, not integers. Now it turns out, oh, we can miss it again. Could you do the thing with that? So it turns out that even though all of these models or all of these diagnostics pass through the same, yeah, no, there will be in a second, pass through the same point, what we see is, if we,
I'm trying to like move the thing, but
yeah, don't worry about it.
without-
Don't worry about it. Just keep going down. Keep going down.
Yeah, it's so critical.
Keep going down. There you go. There, beautiful. You're there. Perfect. Okay.
Great.
So thank you. It turns out that the AUCs themselves, even though it's the exact same point, can be ordered thus. I mean, if you actually do the math, if you actually calculate the AUC, you'd see that, right? So the AUC for B is less than the AUC for A, which is less than the AUC for C. I want to ignore the fact that these curves all cross over each other at different points for now. So just because I know the true positive and true negative, I don't actually know about the power of the models. And I'd like to find that out. So, sorry, I know very little. I know a little bit. Yeah, there we go. So we can't recover the full ROC curve with one point unless you want to make really strong assumptions about normality and these other things, which we usually don't want to make. But we can determine using only geometry an upper and lower bound, which turns out in some cases useful, but also trivial in hindsight. I just want to warn everybody. When you see these pictures, you're going to be very underwhelmed. So here's the theorem. The area under the curve is always greater than the true positive rate times the true negative rate. Again, there's some algebra here, but using some of the relationships we talked about, you can derive that. And the maximum is always less than or equal to the false positive rate times the true positive rate plus the true negative rate. It's entirely possible there's an algebra error there, but I think not because I actually worked it through. But if somebody finds it, I'd be grateful if there is one. So these two theorems now, I can actually calculate bounds on the AUC, even though I only have a single point. Again, these are geometric, or for the time being, I'm not talking about Taylor expansions to figure out the variance and all this stuff.
Looks like you got the area of the rectangle in the top thing.
Ding, 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 ding. Now, we can do better. If we force, by assumption, the curve itself to be above the random line, so it's a useful model, and we force it to be monotonically increasing, we can do a bit better on the bounds. So let me first start with a case where we don't know that. So I'm going to focus on theorems 1 and 2 first. So there's our point. And there's the min and max, which is basically what Lisa said. It's two rectangles. Underwhelming, right? But accurate. And by the way, the min, I don't know if I can use a pointer here. The min up here, you see that there's a little bit of a blue thing there. That's just to show you that at the very end it jumps up, but it's infinitesimally small. And we can even get the expected value because we can, if this is our point, we can assume that effectively there's no differentiation by the model between this point and that point. So we get this little triangle here, and that gives us that other result. If they're well behaved, we can do a bit better. Because in the case of the min here, we get a bit higher min than that one because we're forcing monotonicity and we're forcing the thing to be above 0.5. So those are those results. Here's a quick example. Whitman et al. And et al. And all, by the way, is like 50 names.
All those papers have so many options.
Well, medical ones do, yeah. They evaluate the performance of 12 serological tests, the kind that we buy in the drugstore or that the government sends us. But they did this before they were doing that. For detecting COVID antibodies. They designed a really cool experiment. They took a bunch of specimens from patients that had PCR results that confirmed that they had COVID. And then for control, they chose a bunch of patients whose samples were taken before the COVID epidemic for negatives. It was very clever, I thought. And in each case, they used the same set of biological samples to evaluate each model. Here's the table, one of the tables they produced. This is telling us the specificity. Sorry, the sensitivity. And I want to focus on just two of these because it illustrates the point I was trying to make earlier. We look at biomedics and give a check. there at 20 days out, we get the highest numbers. Now we know most people do the test here, and so we get different results, but sorry, here being 6 to 10 days or 1 to 5 days. But let's say we're focused on the 20 days now, and we get these
20
different,
days, sorry, 20 days from when?
from the time you actually are exposed to when the test will give you a result. So I wait 20 days after I'm exposed, and then I do the test. Or I wait 1 day after I'm exposed and then do the test. Now we know through medical research that 1 day is not enough.
Yes.
5 days might not be enough. We're being told that 6 to 10 days might be enough, but we don't know. So I used this before we knew all that. I mean, I developed this example before we knew all that. And so what I have here, well, I've got 2 of the numbers I need. True positive rates for each test. And now I can do the same thing using the data that was collected, or the samples that were collected before the drug, the pandemic started. And again, I take biomedics and give a check. And I get these 2 results. These are my true positives. Sorry, true negatives. So I can combine those 2 things and make a little table that looks like this. Here's the biometrics and here's the vivid check. And that's the result I was trying to show you earlier, but now it's in the right order.
Yeah.
So what's interesting about this is no model is clearly dominant of the other model. We could ask the question, what if biomedics had chosen 0.9 here? What would this number look like? But we don't know the answer. We could ask the question, what if Vivicek had chosen 0.87 instead of 0.95 as a cutoff? We don't know the answer.
Yeah, that's-
But we can get the upper and lower bounds at least. Yeah? So here we go. There's the min and the max of those by those formulas that I showed you, those really simple geometric formulas. And the difference here is relatively significant. Now, we can ask the question, and I think, Bob, again, you presaged this, this example by 5 minutes or so. What if, in this case, the results are right in the middle? We don't know. We can ask the question, what's the worst thing that could happen if I chose the biometrics test and I used that one? I didn't use the Vivicek test. And the difference is between the max of Vivicek, which I could have achieved, and the minimum of biomedics, which I will, in the worst case, achieve. And that's 26 points of AUC. That's huge. Yeah. Worst case, if I go Vivicek, that difference is 0.14. Even though this is not necessarily an optimal decision, there's a lot of information here that would suggest I might be better off by using Vivicek.
Amazed before that this stuff isn't around all the time.
This was the one that I was really surprised on.
Very
I actually sent this around like a little on a napkin. I'd written it out.
Yeah.
And I was shocked. People came back and said, nope, that's a new result.
Really great. Roger, I'm going to ask you to wind down because I want to ask people if they have questions.
Sure. I'll just very quickly show the last real quick example,
Okay.
and then I'll be done. I'm not going to go through all the math in this case, but if we do the same sort of analysis using this published data, we get this. Another, again, very strong result. But these are now 2 different tests. It's biometrics and Shore, I think is the name. And they're again, bioperfectus, I'm sorry. Decision is fairly clear. So that's it. I will mention that using that result, these results, it turns out that there's all kinds of cool things that we can do about things like correlation between goods and bads and correlation between models and so on that I'm not going to have time to go into. But I'll show you a few quick theorems here. And this is still a work in progress, as I mentioned. There seem to be a number of useful results that take advantage of one or more of the results, as I mentioned. And any comments are welcome. If you'd like to contact me because you find a mistake or you've got an idea, please feel free to do so. There's my info. I'm sorry for starting late because I'm basically, because we were having this technical issue, it took up 20 minutes, which would have been Q&A.
No, this is really great. So we're going to post the recording so we can reacquaint ourselves with the material, but also you said you have working papers.
Yes.
And they're not ready yet. But when they're ready,
Yes.
I hope you will send them to us and we can
Well-
post them too, because I mean, there's 2 things here. One is that the results as they are already look very useful, and they also open doors for extensions that also look very useful. but
Yes.
Will be less useful with one more section. Still,
Thanks for the kind word. By the way, you do have an early copy of the working paper. I'll send you an update
send me
for
another.
comments.
Yeah, I generally always.
Yeah, I know.
But I-
Seems like maybe John might have a.
Yes, John. Hey, John, do, how you doing?
Okay,
Can we hear you?
Roger.
In here from here.
not easy. I get it picked out, so,
Yeah.
John, you want to try again, real quick?
Hey, Roger.
Hey, John.
Just saying hello.
Oh, hi.
So, thank you.
Thanks, guys. Sorry we got started late. I hope some of this is useful. Please give me feedback if you have it.
We totally will, but. we're
Thanks.
gonna, Put this down and look forward to seeing.
Shall I
you
stop the
next
share?
week.
Yeah.
And Roger, I am gonna
Thank you.
give you.
Okay, I like that. So I can teach my class. I have actually another class to teach.
Yeah,
Than what you.
I don't know.